Alright, hi, I'm Whit. Thank you for checking out Space Grant's new robotics workshop. I'm really excited to get into it and I hope you have fun and learn something here today. In this lesson we're going to be looking at the conceptual design of our rover and a few different components that make it up. We'll briefly discuss some manufacturing options to make parts for our rover, and by the end of this lesson we'll have a complete rover chassis ready to accept our electronics. Be sure to check out the Robotics Workshop GitHub page. There's a discussion page there if you have any questions. You can put them there. I'll do my best to answer quickly. Otherwise, you might get some help from some fellow Robotics Challenge participants. Alright, let's get into it. The rover we're building for this workshop is called a differential drive rover. That's because it has two driven wheels, one on the left, one on the right, and they control all motion. Any other wheels on the robot are simply to keep the robot stable. They're often called caster wheels or caster balls. This drive type works great on smooth indoor surfaces because it can turn on a dime, called a 0-point turn. It's nice and simple. In more challenging terrain, you may want to explore other drive types that can offer more traction and stability. Later, we'll want to precisely control how our rover moves. To do that, we need to understand how turning each of its wheels affects the overall motion of the rover's body. Let's consider a rover moving along this curvy dashed line. At some point, you come along and take a snapshot of it from above. At that point, that rover has some linear velocity, forward and back, and some rotational velocity, left and right. A differential drive robot can move in those two ways. It can go forward and backwards and left and right. And so we say our rover has 2 degrees of freedom. What we really want to understand is how our 2 degrees of freedom, our linear velocity v and our angular velocity w, relate to the angular velocities of our left and right wheels, phi L and phi R. To do that, let's recall the relationship for rolling motion. We have a wheel here with radius r and angular velocity phi dot. In that case, the linear speed of our wheel, v wheel, will equal radius times angular velocity. Believe it or not, that simple relationship is most of the literal equation. But our wheels don't exist in isolation, they're tied together by a rigid chassis. So let's consider 2 special cases to think about how that affects things. In the first case, both of our wheels are turning forward, meaning that our rover has only a linear velocity in the forward direction. In this case, because the chassis is rigidly tied to the wheels by the motor axles, the velocity of the chassis will equal the linear velocity of the wheels. That means we can relate the linear velocity of the chassis to the angular velocity of the wheels in the same way that we did before with that wheel speed relationship. By inverting this equation, we can show that the angular velocity of both wheels will equal the velocity of the chassis over the radius of the wheels. In our second special case, the wheels move in opposite directions, causing our robot to have no linear velocity and only an angular velocity. In this case, we can think of our robot altogether as kind of a wheel of its own. By applying that wheel relationship, we can show that 1/2 the distance between our wheels times the angular velocity of our robot's body is equal to that linear velocity of our left wheel or the linear velocity of our right wheel. From this relationship, we can show that the angular velocity of our right wheel equals 1/2 the distance between our wheels times the angular velocity of our chassis over the radius of our wheels. The angular velocity of our left wheel is just the opposite of that. By combining the equations we just derived from our only forward and only turning cases, we can get the inverse kinematics for our robot. These are called the inverse kinematics because for a set of given outputs that we want, they get us the inputs that we need to give to our system. From these inverse kinematics, we can do some linear algebra and get our forward kinematics equations. These are the forward kinematics because they do the opposite. For a given set of inputs, they tell us the outputs we're going to get. Alright, for those of you who followed along with this discussion of robot kinematics and you feel comfortable with all the math we just discussed, great work. This is complicated stuff and it can be challenging to understand. So if you don't feel you understand it, don't worry too hard about it. We're going to revisit this stuff later. We're going to use it in some of our robot motion code. but you don't need to understand exactly how I got to the forward and inverse kinematics equations in order to apply this stuff down the road. I encourage you to continue looking into it. Kinematics is an important subject to understand for robotics, but you'll be okay continuing with this workshop, even if that was confusing. If you were confused by this discussion, I recommend going and checking out our Jupyter notebooks. You might be able to work through it a bit slower. There are better graphics. I know that some of the whiteboard stuff might have been difficult to read, but thank you for bearing with me. Our rover needs to do a few things. The most important among those are move and stay in one piece. By selecting a differential drive system, we've already described how our rover is going to move. It's going to have a left wheel and a right wheel that control all motion, forward and backwards and left and right. If we have two driven wheels, we need two motors to drive them. We need a caster wheel to keep our robot stable, and with all these parts, we need a chassis to connect them. Most of these parts should be in your robotics kit, but one part you may not have already is the chassis. That's not a problem. We're going to talk briefly about how to make a chassis. A great CAD tool for designing your robot is Onshape. It's free for student and hobbyists, and it runs in a browser so you can use it on any computer. We'll be using Onshape for the workshop, so if you don't already have an Onshape account, go ahead and make one. We won't be diving into how to design parts in Onshape at the moment. That's a pretty big topic, but if you're interested in it, it's a very useful skill, and you can find tutorials online for how to do that. For now, I want you to go into Onshape and type in the search bar COSGC Robotics Workshop Rover Chassis. Click right on the document that comes up and hit Copy Workspace. Open that workspace you just created. Along the bottom, there will be 7 tabs. The first 2 are named Rover Chassis and Rover Assembly. You can check out these 2 tabs to see the rover that we're going to make. You can click and drag or use the navigation cube to check out different views of the rover. Click on these tabs or any others you want to explore the design. A rover chassis really doesn't need to be complicated. In this case, it's a flat plate with bolt holes to allow us to mount our parts. This part lends itself really well to laser cutting, so that's what we're going to talk about first. Laser cutting is a process that uses a tool head equipped with a high energy laser to melt through material. By moving the tool head along a predefined path, you can cut out really complex 2D shapes. Laser cutting can't produce 3D parts, which is a limitation of the method, but for 2D parts like our chassis, it's a really quick and really high quality process. Usually laser cutting begins with a DXF file. To export a DXF file from Onshape, click on Sketch 1 in the Rover Chassis tab and select Export as DXF/DWG. Click Export in the resulting pop-up menu and save the file to your computer. So different laser cutting setups will require different processes to run them. If you'd like to laser cut your chassis, I recommend you reach out to someone who has a laser cutter and knows how to use it, who can walk you through the process. The broad strokes generally, though, are going to be you upload your DXF file into a vector graphics editor such as CorelDRAW. You set some print settings and let it run. So if you don't have access to a laser cutter, there are other ways to create your chassis. 3D printing is a great one. These days, a lot of public libraries, schools, even friends who are just into the hobby have 3D printers. They're all over the place, easy to use, ubiquitous. Making a part from a 3D printer with Onshape is pretty simple. In the Rover Chassis tab, right-click on Part 1 and select the Export option. Make sure to click STL in Format and then hit Export to continue. To 3D print, you need a program called a slicer, which creates a toolpath for the printer to follow from an STL file. Slicers can look intimidating, but they're usually pretty easy to use. If you're unfamiliar with 3D printing, I recommend you find someone who is familiar to walk you through the process. In my case, here at Space Grant, we have a bamboo printer, and I'm going to use the bamboo slicer. All I need to do is drag in that STL file we just created, make sure it's scaled properly, and align it on the plate. At this point, I can hit Slice Plate, and it generates the toolpath. I can export this plate-sliced file and put it in my printer and 3D print a chassis. We now have all the parts we need to build the rover, including our chassis, so it's time to put it together. The first step is to put the tread on our tires. This is pretty simple. Just get the lip of the tire over the wheel, slide it on. Now we need to slide our wheels onto the motor axles. It's important to notice that the motor axles are D-shaped. They have a flat side. The wheels also have this flat side, and so you're going to need to make sure that the motor axles are indexed properly with the wheels. This prevents the wheels from slipping when the motor turns. Be careful as you slide the motor axle onto the wheel. Be sure the flat sides of the motor axle is indexed properly with the flat side of the wheel hole. I find it helps to use a screwdriver to pry the wheel apart just a smidge, and then you can slide the motor axle on easily and gently. You don't want to press too hard, otherwise you can damage these motors. So be gentle, use a screwdriver, it makes life easier. Next, we're going to get our motor brackets. We want to get 4 bolts and 4 nuts in order to attach these. If the gearbox extends out past this white motor bracket, you're doing it wrong. It should nestle in there perfectly. You want to make sure that the front of that gearbox is flush with the end of this white motor bracket. Mounting the motors incorrectly like this will affect the performance of your rover down the road, since, as we described in those kinematic equations, the behavior of our rover depends on how far apart our wheels are. So I find it's easiest to sneak a nut down in there. Use a screwdriver to help you get it in place. Yeah, still quite tricky. That's okay. That's life. Make sure you're not getting cross-threaded like me. Go, that one is secure. Now I need to find. Perfect. Okay, so if you're struggling with this, don't feel bad. I'm struggling too. You can see how I got that gearbox improperly aligned. You can loosen it up and kind of wiggle it into place if that happens to you. Perfect. I now have both my wheels on. Alright, next we're going to do our caster wheel. The black caster wheel housing is attached to the underside of the chassis in a similar way. You see these long screws here and these shims? We can get rid of them. We're not going to need them. We're going to use these short screws and no shims. We're going to use a screwdriver to pop that caster ball out of the housing. Be careful so you don't hurt yourself when you do that. And set the caster ball aside for a minute. This housing we want to put on the underside of the chassis, so here where there's nothing else. What we're going to do is stick these screws right through these holes. Be a little challenging, but that's okay. I got it. Wasn't too bad. Alright. And press them down. Might require a little encouragement. Yeah. There we go. And then on the top side, we're going to attach the nuts. Those can go on there finger tight. And we're going to want some pliers to tighten those. I'll be right back. Oh, I'm not going to be right back. Look at that. Pliers right here. You can come at it from one side with a screwdriver, and from the other side, you hold it with some pliers. Perfect. Now it's not going anywhere. Once I'm done, flip it over. Pop that ball back in. Now we've got a chassis. We got wheels, motors, our caster ball, which can slide around. Cool. Next we're going to stick down our breadboards. The underside of the breadboards has yellow sticker paper on them. You can peel that right up. Uh-oh. be a little challenging. So do a better job than I am. Cool, that's gone. I like to line it up so the Pelolu logo is at the back against the back of the chassis. Stick it right down. Perfect. Alright, and now our mini breadboard. Our mini breadboard we're going to do in the same way. Peel off that yellow sticker paper, set it aside, and stick that sucker right down. Beautiful. So now we've got to solder our motor cable connectors. These guys can be a little tricky, but I'm going to show you a trick to do them easily. First, you got to get some pin headers, snap off a set of 6. Beautiful. Yep, that's exactly what I want. So what I'm going to do is I'm going to stick these pin headers down in that breadboard. I'm going to set those on there. I'm going to go run and get solder because I was dumb and didn't grab some before recording. So what you're going to do to solder these pins on easily is you're going to first solder one pin joint real nicely. In this case it's actually pretty good, but in many cases this board may be drooped down. So what you're going to do after soldering only one joint is you're going to come back with the iron, reheat that joint, and adjust it the way you want. There we go. Be careful when you're doing this. If there's if all these pins were connected or something, my hands could get quite hot, and that would be bad. So I've got this part set at the angle I want it. Now, and only now, am I going to come back and solder the rest of these joints. Perfect. Easy as that. So I'm going to go do the other one real quick. Alright, now we're going to place our first components on the breadboard. So first, take one of the motor connectors and a motor cable. Plug the motor cables into the motor connectors. You have to fidget around with it. Don't force it. There is a correct direction. You can see I had to double check to make sure I was doing it in the correct direction. It goes in quite easily when you do. Next, take a motor connector and plug your first motor connector into A1 through 6 on the breadboard. You can see the breadboard has letters and numbers, and that just went into A1 through 6. Next, I'm going to take the other motor connector and plug it into J1 through 6. In either cases, you'll notice I've made sure that the red wire from the motor cable is going forward. That's going to be important later. Alright, so last, let's get out the Arduino Nano. In my case, the pin headers are already soldered on, you can see. But if they're not soldered on, then I want you to do a similar process to what we just did with the motor connectors. You're going to take these pins, you're going to insert them in the breadboard, set this Arduino nicely on top, and solder all the pins. But since mine are already soldered, all I need to do is place this guy on the breadboard. So what I'm going to do is make sure that the USB connector on the Nano is facing downwards. I'm going to press this left row of pins into D16 through 30 and the right row into H16 through 30. Alright, this one can be a bit tough. There's a lot of pins, so there's a lot of friction. Just be gentle with it, work it in there. Yeah, this guy's fun. now it's in. Now I haven't connected my motor cables to the motor yet, so I'm gonna go, finally, I'm gonna do that. Again, make sure that the plugs are facing the right direction. And we are good to go. Alright, with that, we're done for today. I'll see you in the next lesson where we're going to use this platform we built today to learn more about robot circuitry in motion. Before long, we're going to have your rover roving all over the place.